Hi everybody, welcome to the lesson on normal distributions. So in this lesson we're going to review some of the basics of normal distributions, and we're going to talk about also how do you determine whether a data set follows approximately a normal distribution. We're doing this lesson for a couple of reasons. One is that normal distributions form the basis of so many of the inferential methods we'll do throughout the course. And as part of that, a lot of the methods that we use they have an assumption that the data that feeds into them follow a normal distribution. So you can see that that's going to be pretty important to us. Before we start talking about the normal distributions themselves, let me mention that normal distributions are continuous probability distributions, and that means that the values you're finding the probability of, so if I want to find the probability that a given value is selected, that given value is on a continuous scale. Meaning if that value is somewhere between 2 and 5, it can be any value in there, any real number, including values like pi that are irrational. So it can go out to any number of decimal places. The implication of that, with there being so many possible values that could be chosen, is that the probability for any given one of those is 0, because there are so many of them. An analogy I've used before is if I took a grain of sand and put it somewhere on a beach, somewhere on the earth, and had you go pick up a grain of sand somewhere on the beach, somewhere on the earth, the probability that you would pick up the same one I left behind would probably be pretty close to 0. And that's what we have going on here. So the probability that x equals some particular number is 0. As a result, we don't talk about the probability that x equals a value. Instead, we talk about intervals of values. So instead, we might look at the probability that x is less than some number, or greater than some number, or between two numbers. And since the probability x equals some number is 0, it doesn't matter if you talk about less than versus less than or equal to, because the equal to just doesn't make a difference. Same thing is true if you talk about the probability greater than. That's the same as greater than or equal to. Also, in general, probabilities correspond to areas under the curve. And what I mean by that is if you've got your probability distribution, and say, just for the sake of, let's just say it looks like this. The probability between this value and this value is the proportion of the area under that curve between those two values. So now on to normal distributions. Normal distributions are, and you can tell I'm referring to them in the plural, that's because they're considered to be a family of distributions, where every combination of the mean and the standard deviation is a different normal distribution. So the normal distribution is bell-shaped. All of them have a mean of mu, Mu can be any real number, negative, positive, or zero. And the standard deviation can be any real number as long as it's greater than zero, strictly greater than. This is the formula for the normal distribution, and I'm not suggesting you write this down. You don't need it for anything. The reason I put it in here is just to show you what it looks like, and because if you're a student who has had calculus, when we're finding the area under the curve, you might be wondering why we're not doing the integral. And this is why, because this function, you can't take the integral of it. So now about the standard normal distribution. So the standard normal distribution has a mean of 0 and a standard deviation of 1. So that's the standard normal distribution. Is of all of the possible normal distributions, this is the standard one. This is the one that all others refer back to, essentially. It's important enough it gets its own letter. So it's z and not x. So the normal distribution, I guess I should talk about this picture a little bit. Mu is in the middle, and we usually sketch out 3 standard deviations in either direction, even though it theoretically goes out for infinity in both directions. It's just that this gets infinitely close to the line, the axis. So we usually stop sketching at 3 and negative 3. So for the standard normal distribution, the mean is 0, so 0 is in the middle there. And you've got 1, 2, and 3 standard deviations below, and then 1, 2, and 3 standard deviations above. Now, there are a lot of ways you can find standard normal probabilities. There's technology that you can use, and I let my intro classes do that. But this isn't an intro class, and I think it's important enough that I'm going to have you use the table. So I think at this level, you should be exposed to the normal table. So this is one format for a normal distribution table. There's other versions of this out there. But, so you've got different values of z down the side. These are negative on down to 0, and these start up with 0 and go positive. And this table shows a little beyond negative 3 to 3. So the column shows the whole number plus the first decimal place, so the tens place. And then up here, this shows the hundredths place of the number. So this number here, 0.0002, refers to negative 3.49. Okay? Whereas this one over here is negative 2.40. And if you see the way these are shaded, this kind of tells you how to read the table. If you look up the z value, that's this value down here, or this value down here, and the shaded area is the area to the left of z, and that's the value you're finding on the table. So, for example, probability that z is less than 2.45. I think it helps to sketch these. So I'm going to have you sketch these. That looks terrible. But So there's 0, 1, 2, 3, and then negative 1, 2, 3 on the left. But we just need up here, so 2.45 is going to be right about here. This is less than, so we want to shade to the left. So we're looking for this area over here to the left side of this line. So if I look up 2.45 on the table, here is 2.4, and I'm going to make this just a little bit bigger. Maybe not quite that big. So 2.45. This column here is 0, 1, 2, 3, 4, 5. So 2.45 is 0.9929. And that's because this column has the 5, so the 5 is the hundredths place. So 2.45 is 0.9929. And that is this shaded area there. And you can kind of see from looking at this that looks about right. The area under this whole thing is 100% or 1. So this area, 0.9929, should be a pretty big chunk of it. So that should be most of what's under the curve. And you can see a little better in this version. 2.45 is right about there. And you can see that is about 99%. That can be a sanity check when you look at your graph and see if the answer looks like it makes sense. So what if I wanted to do a greater than probability? There's 0 in the middle, negative 1, negative 2. So negative 1.38 might be right about there. And I'm looking for the area this time to the right. So that's this whole area here on up. So the table is in all the values on the table tell you below. So if I want greater than, keep in mind that this whole thing under the curve is 1. So whatever value is to the left, if I do 1 minus that, I'll get the probability above. So if I'm looking for negative 1.38, double check and make sure, yep, negative 1.38. 8 is this next to last column here. So negative 1.38 is going to be 0.0838. But the 0.0838 is this area down here. So to get this area up here, we have to do 1 minus that. And I'm just going to use the little calculator. So 0.9162. And again, I think you can tell by looking at that looks about right. Now, a lot of times we'll want to do a between probability. So the probability that z falls between two numbers. So I'm going to sketch this, and 0's in the middle, -1 is about here, and 1 is right about here. So I'm looking for the area between those two values. So what I'm going to do is I'm going to find the area to the left of 1. So here's 1 and here's -1. I'm going to find this whole area here to start with. So if I look up 1 on the table, so 1.00, that gives me 0.8413. And I'm going to subtract out just draw on here. I'm going to subtract out this part of it. So if I take this whole area to the left of 1 and I subtract out the area to the left of -1, then I'll have the area I want. So if I look up 0.8413, or if I look up, I'm sorry, -1, -1.0 gives me 0.1587. So if I do that subtraction, that'll give me the my answer that I'm looking for. 0.8413 minus 0.1587, and that's 0.6826. So that's finding standard normal probabilities. We may also want to find inverse standard normal probabilities, meaning we may want to be able to find the value of z that corresponds to a certain probability. So for this first one, we're looking for some value c where 25% of the area is to the left of it. And because this is less than half, half would be right here in the middle. It's got to be to the left of the middle. So that's telling us this area is going to be 0.25. So we just go to our table and we look up 0.25 in the middle and we find the closest value of z. So I'm going to look up 0.25 in the middle. And that's right between these two. So that's negative, so that's on the -0.6 row. So -0.6, and it's between these two columns. So it's between negative 0.67 and negative 0.68. So if you want to, you can split the difference there and call that negative 0.675. So negative 0.675. For this greater than, we're going to do the same thing, except if we've got 13% above this value of C, we've got to convert that to a less than. So we're looking for 1 minus 0.13 or 0.87 to the left. So we're going to look up 0.87 in the middle of the table. And that is, the closest thing to that is 1.13. This one's, the other one was right about halfway. This one's closer to this second one. So I'm just going to go with 1.13. I'm not going to be super strict about that. That's supposed to be 1.13. My mouse pen is not cooperating. And finally, the value of C with 92% in the middle. So the thing to keep in mind here is if we've got 92% in the middle, that means we've got 1 minus 0.92, which is 0.08, in the tails. And we've got half of that in each tail. So 0.04 in each tail. So that means we've got 0.04 here and 0.04 up here. So if I'm looking for this value of C, I'm looking for the value with 0.92, so this 0.92 plus this 0.04. So I'm really looking for .96 if you add those two together. And it's always going to work that way. So we're going to look up 0.96 on the table. So 0.96. The closest thing is 0.9599, which is 1.75. So our answer is 1.75. And then this value over here to the left would be negative 1.75. But these are the same, it's just one's negative and the other one's positive. So it's fine to just state the positive one. All right, so that's it for the standard normal distribution. Now let's talk about non-standard normal distributions. These are ones where you've got any other mean standard deviation combination. And these are what you'd see, more in a real life situation. So let's first look at how to find normal probabilities. On all of these, we're going to be using the conversion that we've talked about before, where the relationship between x and z is x minus mu over sigma. So on all of these problems, we're gonna use the example that high temperatures in June follow a normal distribution with a mean of 82 degrees and a standard deviation of 4 degrees. So we're looking for the probability that on a randomly selected day in June, the high temperature, which is x, and it's not z because the only time it would be z is if the mean is 0 and the standard deviation is 1, is between 75 and 85. So all we have to do is convert the 75 and the 85 to z. And that's because if you, I'm going to go back up and look at this. For the non-standard normal distributions, we're looking at this picture. You could, if you wanted to, put in a second axis down here. And this lines up with 0, 1, 2, and 3. And then -1, -2, and -3. And these are just on different scales. They're the same values, they're just on different scales. So all we're doing is we're going from one scale to the other using that conversion of x minus mu over sigma equals z. So I'm going to take 75 minus the mean, which we know is 82, divide by the standard deviation. And you could think about it as, you know, converting here just like you're subtracting the same number from both sides, except we're doing it here all three places. And we're just subtracting the mean and dividing by the standard deviation everywhere. And sigma has to be positive, so we don't have to worry about changing the direction of the inequality. If you're algebra savvy, you may have wondered about that. So 85 minus the mean over the standard deviation. And now we've got all values that are, they're all converted to z. So 75 minus 82 divided by 4, we get negative 1.75 less than z less than 85 minus 82 is 3, divided by 4 is just 0.75. I don't need to compute that. And then we just go to our normal table. So our normal table, using the same logic as we did before, I'm looking at 0.75 first. So 0.75. So that's 0.7734. Minus the lower one, so negative 1.75. If I were you, I would print this table, because I know for me it drives me a little bit batty trying to use it on the computer. So negative 1.75 is goes with 0.0401. And so we end up with .7333 is the probability. Right. I'm going to guess you don't need the second example. Maybe you want to try it, and if you try it, I will confirm in class whether you got it right. And let's look at maybe the second one of these. What temperatures make up the middle 70%? This is going to be an inverse normal probability because they're asking for the temperatures that go along with a certain probability. So in other words, they're asking for your two temperatures where 70% is in the middle. So to do these inverse normal probabilities, we're first going to find the z values, and then we're going to convert them back to x using this equation. So let's first find these two values on the normal table. Sorry, I'm going to sneeze. So let's look at the normal table, and we're looking for the middle 70%. So the middle 70% means that we've got 0.15 in each tail. So we are looking for 0.85 because that's this 0.7 plus this 0.15. So 0.85 in the middle of the table. .85 is right about here, so 1.04 is the closest. And we've got two different values here, and when you're stating them as z's, it doesn't matter. But if you're going to plug them into a formula like this, we need the plus or minus. So in this case, z is plus or minus 1.04. And this time we don't have x, but we do have z. So we're plugging in for z. We've got mu and sigma, and we're going to solve for x. So x minus the mean we said was 82, and the standard deviation is 4. So I'm just going to solve that for x. So 1.04 times 4 is 4.16, and this is still plus or minus. And that's x minus 82. So if I add 82 on both sides, that's 82 plus or minus 4.16. So 82 minus 4.16 is 77.84. And then 82 plus 4.16 would be 86.16. All right, so that's it for our review of how to find normal probabilities and inverse normal probabilities. Stay tuned. In the next video, we will talk about assessing normality.